Okay, let's continue by the second part of this. I'm going to calculate the PSM for the relay number two. Since the fault current is 5,000, means relay two, of course, is a backup. So PSM for the this time is for the relay two is as a backup one, as a backup relay. It is not for the fault at this point, which is in front of the relay. Be careful. We know that one PSM 5000 over this one. The PS again must consider as a maximum since we don't know the current of the means the load current times here we should times it by the PS or overload factor, which is considered as a 1 2.5. So it is clear the value for this one is 5000 sorry why 5000 is 25, no, it's 5 divided by 1 2.5, which is 4. Okay, we get it. It's 4. So using the table, the same table, where are you table again? If it's 4, operating time, if it's 4, if PSM is equal to 4, using the table, okay, the operating time based on this table for the TSM equal 1, for this one is 5 second, 5 second. So to calculate TSM is the given value means the calculated value here as a 1.7, I think, is it? The real one. Yeah, 1.7. Okay, this is as a backup. This is calculated one divided by 5. So you can use your calculator and find out what is the final value. 1.7 divided by 5 equal to 0.34. 0.34. And this question is already answered. Done. Okay, let's go and see question example 5.3. There is a reason I cover this one after 5.4. Since here it's mentioned I'm talking about a transformer. Okay, when we have a transformer, let before starting this example, let me show you the single line diagram of this. Control A, delete. Okay. The single line diagram of this example is coming in this way. We have a transformer. The transformer is in the way, and this is one switch, means one circuit breaker. This is the other circuit breaker. The transformer is 20 megavolt amp. Okay. 11 kV as at the secondary side. I'm not sure about the primary side, nothing mentioned. So overload is given. Overload 25% more. So it's 1.25 overload factor. Okay, correct. The CT given here is called feeder. Feeder. Here is for the circuit breaker of the transformer. So let's see. It mentioned that the transformer circuit breaker is equipped with the CT 1000 to 5, and then the other one, the feeder one, is 500 to 5. 500 to 5, and then relay feeder circuit breaker plug setting feeder 1. The PS or overload for this one is 1.25, so it's already covered, and TSM for this one is equal 0.4. Fault current at this point is 7500 amp. Again, they ask to find out the settings for the discrimination time also given. Again, 0.5 second. Find out the operating time of the relay, this relay, and this relay, and the TSM for the other relay if possible. Here we have a note. I ask you to somehow change this paragraph from answer to the question part as a note. For the transformer, okay, the PS for the transformer are always considered as a 1.25 or 125% or 150%. Why? Because of, if you go to this part, power transformer impact over current relay, you can see it mentioned by here. If you review this one, as I mentioned also in the class, okay, and covered by this example, you can see, okay. So mostly they must be chosen as 150. So PS for this transformer also is considered as 1.5. Okay, let's do the calculation for this transformer, for this relay. Okay, step one, PSM for the relay number one is the fault current, which is 7,500 times what is the CT ratio here is 5 over 500, correct. The current at the secondary of this one is 5 again times 1.25. So the value here is coming out as, oh, don't forget, for the graph characteristic relay, time relay characteristic, we should using figure 5.4, which is this one, okay? So 7,500 times 5 divided by 500 divided by 5 times 1.25 is 12. So using this graph as 10, 11, 12, assume this is 12. Something around 3. So assume using the graph, okay, the operation time for the TSM equal 1 as a main relay is 2.8 seconds. So we need it for the 0 0.4, 0. What is the time for this one? We need it for 0 0.4, correct. So the real operating time for the main relay by the given TSM is 2.8 times 0 0.4, which is 2.8 times 0 0.4 equal 1.12 second. Okay. Then, since we know we are going to coordinate these two relays with each other, the operating time for the backup relay for the fault at this point is, so operating time, okay, for the backup relay, it's 1.12 plus discrimination time, which is 0 0.5, correct? It's 1.62 second. Okay. The other things we have to calculate is, it's okay. PSM for this relay is equal fault current for the relay number one for the front relay times CTR. For this relay, CTR is 5 over 1000, if I'm not mistaken, correct? Yes. PS for this relay 1.5 times 5. Okay, so it's in fact is 7.5 divided by this one cancel, 1.5. It's 5. It's 5. So again, using the graph, where are you graph? So the graph is here. It's 5. It's something 4 point something. So using graph, the operating time of the relay, backup relay is 4 point, assume 4 point, I'm not sure, it's 4.8. It's not very uh, accurate, but it's okay. Then the TSM, since this one is the real one, since this one is the real operating time, okay? This one is given by the TSM equal to 1, correct? What is the correct TSM for this relay? It is 1.62 divided by 4 is it 8? I mentioned 8. So the TSM coming out as a 1.62 divided by 4.8. So it's 0.337. So I assume it's 0.338. Done. What is the value selected by here? Is this one 5? 0.3, oh yeah, okay, 45. Because the selected value based on the graph is a bit different, but the answer is acceptable for both. Then next example, which is aligned with your lab 2, and the final project one is this example. So you must be very familiar and understanding very well the example. This example in the given one, there are lots of for this one. We have lots of problem based on my understanding need to be revised. So I already do and ask you to also following this revision for your case. Let's see the example. The figure is given 5.14. This is the graphs. This is the figure. So we have one substation, which is short circuit is given. Short circuit power is given. Then we have a transformer. Then we have a transmission line and three loads. Since the given one, these two loads, the value is not mentioned, so we can ignore them. Okay, go back to the question, a big one. Calculate the nominal current, three-phase short circuit. Select cities, determine the pickup setting, time deal setting, and instantaneous setting of the relays. And then discrimination time is considered as 0.4. Another things you have to consider this one for the graph of the relay, operation graph of the relays. This is operation time, this is PSM, and this is time deal setting. Next, pickup setting cannot be it's given as a discrete value from 1 to 12, so you can only choose 1, 2, 3, 4, 5, 6. The steps are in one. Time deal setting given by this figure, yeah, I mentioned. Again, instantaneous currents for the relay also must be in the steps of one. So start with 6. We cannot choose less than 6. And the maximum is 144 in the step of one. Relay settings or relay pickup setting set on the 150%. And then what else? The city coefficient, the city's selected value for the city must be coefficient of 100. So we can have 100, 200, 300, but we cannot have 150 or 250 by 5. These are not acceptable by here. So let's start to do step one for this. Where are you? The graph, single line. Okay. For this network, step one, we have to consider the single line diagram. Calculate the fault current. How we can calculate the fault current and impedance of this substation? Can you remember in the per unit we said the Z is equal V power of 2 over S. Since we know the voltage at substation is 115 K power of 2 over S 950 mega. So what is the final value by here? The final values here is 115 power of 2 divided by 950, which is 13.92 ohm. Okay. For the transformer, also is given in the per unit value. Then we can refer it to the high voltage one, which is 115, or the low voltage, which is 13.2 kilovolt. Okay, it's up to you, chosen which one. In this example, we represent both the same as this transmission line. You can see it's given the value of the impedance of the transmission line is given in the 115 kilovolt and 1.125. Sorry, in 115 kilovolt and 13.2 kilovolt. Then also we need to calculate the load current, correct? Okay, let's start. This one I already calculate 13.92. For the transformer, for the transformer, let's consider as a high voltage side. Since this value is given in the percentage or per unit, the same. Okay, Z base for the transformer is voltage at the one side. Right now we consider again high voltage side, 115K, power of 2. This time on behalf of 950, which is a short circuit, we should consider the transformer ratio for the power, which is 25 megavolt amp. So it is 115 power of 2 divided by 25 is 529 ohm. And then the Z transformer in the ohm is 529 times 4.8%, which is 25.392. This is the point here, okay? Is here, okay? The transmission line in the 115, the value is given by here. So no need to calculate. Right now we have to calculate, for the next step, we have to calculate the, okay, this one, Control A, delete. Okay, we have to calculate the current. So relay 1 is here, as you can see, okay? Then I nominal for the relay number 1 is equal 3 megawatt, 3 megawatt. You know the formula, S is equal square 3 V I, correct? This is the formula we need to calculate. So 3 megawatt square 3 times voltage. Voltage at the lowest means voltage at this side for this bus is 13.2. So 13.2 K. The final value here is given as 3 divided by 13.2 times square 3. So 13.12 amp, if not mistaken, correct? 13, oh, yes. It's 132, sorry, I missed a dot. 132.1, sorry, 131.2 amp, okay? 131.2 amp times 10, for me, it's working, okay. Then relay 2 is placed by here. The nominal current is the current of this one plus this one plus this one, since 3 in the same value. So I nominal for relay number 2 at voltage 13.2 kilovolt is 3 times 131.2, which is 393.6. And then for the nominal current for transformer for the relay number 3, since the transformer is there, okay, we must consider the transformer ratio, to calculate the nominal current of the transformer. So I nominal number 3 for relay 3 at voltage 13.2 is equal, here is, what is the ratio? 25 mega over square 3 times 13.2. The value I must be given by here, it's 1093.5 amp. 1093.5. For the other side of the transformer, okay, you can easily using the transformer ratio to convert the current from this side to the other side. So it's 13.2 over 115. Of course, when the voltage increase, the current must decrease, and it is proof by this one. See, this is the current at the secondary side of the transformer, which is here. Okay, the primary side current is less. So right now, at this point, we know the impedances and we know the nominal current of the transformer. Next step is to calculate the fault current for the system. If we redo and redraw the single line diagram of this system, you can see by here, since all the values calculated for 115, you can easily do it for 115. The voltage of the system is 115 divided by square 3 to make it single line, correct? This is the source impedance. So this is the source impedance, this is the transformer impedance, and this is the transmission line impedance. Then the bus is also highlighted for you, CBA. If we have a fault at this point, at bus C, it's very clear what is the fault current. Using a KVL here, KVL, you can see this is the voltage source divided by, means using the Ohm's law, of course it is. So the I, the fault current IF, is the voltage source, which is 115 divided by square 3. This is 13.92 plus 2539 plus 85.35. So the sigma means the total impedance, the total. The fault current can be calculated as a 532.6 amp. But this one is for 115 kilovolt. This value, which is the fault at C, correct? The fault at C for voltage 13.2 kilovolt is equal the same value 532.6 times 115 over 13.2. So the value you can find it out here. Okay, for the bus B, which is here, the fault current can be calculated again in the same idea using KVL. This is the voltage source. We have this impedance plus this impedance, and finally the fault current at B is 1689 for 115, which is 14,715, around 715. Okay, it's quite big. You can ignore that one. And the fault at A, which is here, easily can be calculated. This is the source and this is the impedance. So we no need to change this one to 13.2 kilovolts. Why? Because bus A originally is located at high voltage side. Then you need to make a table exactly the same as this one. Whatever, you can cancel and remove this one. It's not very important, okay? Or you can follow in the same steps of this, okay? So for the breakers, I'm going to choose the CT. As I mentioned in the class last session, face-to-face, the CT selection are done in two ways. The first one, we have to calculate nominal current, and then after using the nominal current, find out the CT. The second one, we should calculate the maximum short circuit current without saturation for the CT. which coming in the way of I short circuit divided by 20. I short circuit divided by 20, or as you can see here, is a 5 over 100. So let's list down and jot down everything in the table. I nominal for circuit breaker number 1, as you can remember, is 131.2. For bus number 2, which is, this is bus number 1, this is bus number 2, 3, and 4. Okay, for bus number 2 is 3 times of bus number 1, 1, 2, 3. So 393.6, yes. For the other, for the breaker number 3 is coming in this way. Yeah, 1093.5. And finally, for the last circuit breaker is 125.5. Then the short circuit current must be listed, and without saturation idea and without saturation testing, which is divided by 20, is listed down by here. So you can see the highlighted one are the bigger or the biggest number in each row. So this is for the nominal current 130 something, for the short circuit without saturation is 200 something. So since we have no CT 250, as mentioned, the CT value must be integer, coefficient of 100. We must choose 300 to 5. For this one, 393 and 735, we should choose 800 to 5. Here is the example. You see, every time we have transformer, nominal current of the transformer is a headache. So the relay here must be, sorry, the CT here must be selected as a 1100 over 5. And finally, for this one is 300 to 5. Okay. Next step is to coordinate and find out the PSM of the relays. Okay. What should we do? Following this formula. The first formula, this is the formula. Okay. We are going to following this formula and find out the values for the nominal current and then pick up. Okay, for all of them, based on the question, the PS or overload factor is considered as 150. You can see 150, 150, 150 for all of them. Okay, correct? The nominal current listed down. This is nominal current for breaker number 1 or relay number 1, relay number 2, relay number 3, and relay number 4. Correct? And then we need to times it or divide it by CTR. It's up to you. I mentioned why. Sometimes it's times, sometimes it's divide, but mostly the meaning is clear. I agree. I have to following one instruction only. So we are trying to reduce the current. Just consider that one. Okay, based on calculation here, we reach to the value 3.28. As you can see here by the question instruction, we cannot have this one, the pickup current. The pickup current is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So it is 3 point something. We cannot choose 3 point something. We must choose 4. So because of that, we upgrade the pickup current to 4. In the same 3.96, again upgraded to 4. Here, 7 point something upgraded to 8. And finally, we have another upgraded to 4. At this point, since we change the pickup current, the nominal one is coming in this way, which the final value is less than 240. You can see it's 131. If you want to know what is the pickup, the real pickup current is 131.2 times 1.5, which is 196.8. Okay, since we upgraded from this value to 4, here we are going to find out what is the pickup current in the ampere. So it's given as a 4. This is 4 times CT, the inverse of the CT or the CT ratio, which is 240. So before that, it must be picked up by something around 200. Right now, it's picked up by 240. Okay. My suggestion to implement these changes in your notes, okay? So time build setting, no need to be there, okay? Just cancel it, delete it. Setting of instantaneous element, since relay number one is the first closest and is the first and closest to the load, the instantaneous element must operate very fast, okay? You can consider zero point 0.5, which is correct one, and it's going to increase the sensitivity, okay? But since you are undergraduate student, I strongly suggest to forget that one, okay? Which is a real practical action. We're just following the normal step instructed by the previous question and inside the notes, okay? So remove zero point 0.5. The PS clock setting multiplier for this one is equal to what? Is equal to fault current. What is the fault current here? The fault current here is 4,640, correct? You can see by here, 4,640. Okay, you list it down. Times CTR. What is the CTR ratio? So for this one, the CTR is selected as a 5 over 300. Okay, it's also done. Then here, before that, we use it 5 times blah, blah, blah. Okay, right now we have the value. The value is given, correct? So this value is 4. So no need to recalculate and do lots of attempts. Using calculator 4640 times 5 divided by 300 divided by 4, you can reach the value which is equal to 19.33. Okay, 19.33. This value again need to be upgraded. Okay, this value again need to be upgraded. Before reaching to this value, we have to upgrade this. Because the setting of instantaneous element, this is the setting of instantaneous element. How we should upgrade, it's coming in this way. 4,000 times by 5 over 300 is a value around 77 point something, okay? Since the instantaneous element, the same as the pickup current, is given in discrete value by 1, where are you? It's here, okay? Instantaneous can change from 6 to 144. Okay, we must see. Okay, we must upgrade from 77 something to 78. Okay, so 78, if you want to see the real value here again, what is the value from? Because we upgraded from 4,640. The real value on behalf of 4,640 upgraded to 4,680. Okay, then 4,680 divided by 4, of course, times CTR, which is 5 over 300, or easily you can thinking about 78 divided by 4, the final value is 19.5. From this value, which is 19.5, we should using the graph. Where are your graph? Graph is here. 19.5. Let me change. 19.5 is already 20 is here. Okay. So for the first relay closest to the load, the operation time of the relay must be minimum. So the minimum operation time of the relay in the power system can be set as a 0.1. Okay. So since I zoom in, you can see it's over than TSM equal to 2. Yeah, here. Just look carefully. You can see it's over. Okay. So we cannot choose 2. Because of that, we have to upgrade this one to the next level, which is here. Okay. So it means that the operation time of the relay on behalf of being very, very fast at 0.1 is something close to 0.15. Here is I assume it's 0.14, maybe 5. Okay, something looks like that one for me. So the operation time of the relay is given as 0. Okay, yes, by 3. So TSM is 0.14 or 0.145. Okay, then by this current, which is 4680, correct? 4680. We are going to this operating time 0.14 is for the first relay. So backup relay, since we know the discrimination time, the operation time of the backup relay for relay 1, which is relay number 2, operation time of relay 2 is equal 0.14 plus discrimination time, which is 0.4. So it's 0.54. Okay, correct. Then by this value, by the fault current at the relay number 1, we should calculate the PSM for the breaker number 2 or for relay number 2. Again, we should calculate the faulty current here. The faulty current here is 400 4680 times the CT. The CT is 5 over 800, correct, divided by 1 over 4, which is this one. 1 over 4, where are you? Is this 4? Yeah, 1 over 4. So the final value here is equal 4680 divided by 800 divided by 4 times 5, 7.3. 7.3. Okay, right now we know the operation, we know the PSM, so we can find out, and we know the operating time as a backup for this relay. So let's find out the TSM based on the graph. So we should put the timing on 0.54 and the PSM on 7.3. 5 point, where are you? Okay, it's the timing is 5.5, around, so a bit less than 5.5, which is here. Okay, assume it's here. Then the other one, it's 7.3. 7 is here. You can see 7 is here. So 7.3 is somehow equal to this, or maybe a bit more. Okay, in my view. So you can see, if you can see, is look like placed on this graph, which is 4. Otherwise, if you don't accept number 4, correct, if you don't accept number 4 as a TDS, you must go for the next one, which is 5. Okay, let me check which one I choose for this. If I choose 4, it's here, I choose number 5. Okay, let's upgrade it. I said number 4 is not working. If you zoom in, of course, it's not working. You can see it's a bit over than that one. Okay, correct. So let's upgrade it to the next level, which is this one. Okay. So based on that one, the relay, the operation time is considered as a 60 something. So the backup relay is a bit, the time of operation of backup relay is a bit higher than discrimination time, 6.5. Okay, as you can see. However, we have to, there is no chance for us. Why we cannot choose it as other values? Because this graphs TDS is given as a discrete. So if you are very interested and very sensitive to the real value, you must choose number 4. And since operating time is not following exactly the discrimination time less than 0.4, or you have to upgrade it the same as something I did. So since it's a backup, it is not a major case. Okay. Next one, since we choose the TDS or time setting multiplier for this one as a 5, let's find out the fault current value when the fault executed just after this bus, means close to bus number 2 or relay number 2. If you check, this table, you can see the fault current must be 14,715, and then based on the given instruction, we must increase it 25%. So 1.25% times the faulty current. I change this one. The CT is still the same. We reach to this value 11496, and then this value is not acceptable. Why? Because 0.96 is not their discrete. Okay, so we should upgrade it to 115, and then the instantaneous unit and faulty current, it reached to 18,400. No worries about that one. 18,400 for the fault in front of the relay means operating as a main unit for clear the fault. 18,400 times the CT over the pickup current become 28.75. Again, we know the TDS, which is 5, and we know the PSM 2875. Let's go. Where are you? Number 5 is here. So 28 is somehow, I think, is here. Okay, 28. And we must make it by 5. We must make it by 5. Is something. Okay, let me make it very. Okay, so you can see the operating time is a bit less than 2. A bit less than 2. So what is the value I selected before? Is 0.195, I think. 0.19, 0.19, 19 millisecond, no, 190 millisecond, correct? Okay, right now for relay number 3, how we should do the coordination of the relay. We know the faulty current, which is this value by here, and again we have to upgrade it and make the backup for the other relay. So it is discrimination time, add to this one 0.19 plus discrimination time 0.4 becomes 0.59. Okay, second, this is the operation time for relay 3 as a backup. Okay, as a backup. And then for the current, the fault current at at the relay number 2, but backup number 3, we have to calculate PSM. In the same way, PSM is 14,715 times the relay ratio. The relay CTR here is 5 over 1,000, 1,100 over the pickup current, which is 8 by here. So the final value is 8.36. 8.36. Again, using the graph, we know the operating time is 59, 8.36. Let's see. Change this one to 8.36. This is 8.36. Assume it's 4. Okay, in my view is working. So operating time is considered as a 59. Assume it's 6. A bit less is here. So which one we can choose? Again, this one cannot be chosen. So we have to go for the other one, which is, wait,